In this video, I will tell you how you can make a fighting game in Godot completely from scratch. We will not only go over importing assets, rigging animations, writing the character controller, adding game juice, configuring state machines, and much more. This series took me a whole month to make, and I'm sure you guys will love it. So, without further ado, let's start. At the end of this video, you will have a game scene set up like this as well as a state machine to manage the player. Let's get started. At first, we have a vanilla Godot project and the sprites that we will use throughout the video series. You can download these sprites from the link given below. I have just extracted these sprites into our game directory to save some time. As part of the setup, we will change our game's resolution to be 720p instead of whatever Godot provides as default. Next, we will provide two physics layers, one for our world like the trees, roads, etc. and one for our characters. With the setup done, let's start making our player, which will be a character body 2D. Next, we will add an animated sprite node to it and add these sprites for when the player will be idling. Now you will see that our sprites are blurred. This is because we have to change our texture filter from linear to nearest. With this, our sprite should look proper now. Finally, we will add our walking sprites before moving on. Now we will add a collision shape 2D to do away with the warning sign next to the player. This collision shape will be used by the player to collide with the world, like walking on the ground, touching the walls, etc. For this, the shape should be roughly around the size of the player. It is totally up to you. It will take probably quite a bit of tweaking to get it right, but for me, this is fine. Okay, with our basic layer done, let's move on to the level. To make the level, we will have to set up our tile map first. For this tile map, we'll make a tile set out of the level sprites that we downloaded at the start of the video. Then in our tile map, we'll make a physics layer with the layer properties set to world and the mask properties set to character. Then we will paint this layer across these two columns of tiles. These will be the tiles that our player will stand upon. Then let us add a camera to the scene with the zoom level set to 3. It can be anything, but I like it at 3. Then let's set a player to the level. Now before painting the rest of the level with our tiles, we will have to first set up our visual layers. These are the layers on which our tiles will be drawn on, and it is primarily used to set up our foreground and background tiles. All in all, we will have 4 layers. One for our foreground. These will be tiles that are drawn in the same visual layer as our player. Then a background layer for all the tiles behind our player. Thirdly, a prop layer for all the tiles above our player. And finally, a backdrop layer to fill the empty spaces in the level. With our layers now set, let's pick the foreground layer and paint the walkable area for the player to walk on. And then on the background layer, we'll put in the non-walkable areas like the buildings and the footpath. With this, our game now looks something like this. Of course, we can't do much. For that, we will have to code in our player now. To quickly test our changes till now, we can attach the default character body 2D script to our player and test the game with it. As you can see, everything works fine. However, we will not be moving forward with the script because if we were, this would not be much of a tutorial, would it? Instead, we will be using the concept called state machines. Stealing from my previous video of what a state machine is, state machine, a mathematical model that defines the behavior of a system to exist in a finite number of states and transition between set states based on a set number of input. Let's take an example. Suppose you have a vending machine, a machine that is currently waiting for you to give it some coin. Once you give it some money, it dispenses your item. Upon a collection of said item, the machine goes back into waiting for you to give it some coins again. What we have here now is a finite state machine having 2 states. 1. Waiting for coin. 2. Dispensing items with arrows to describe the transition between said states. And the reason why we are implementing state machine is because our player will have a huge number of states, and coding all of them in just a single file is not for the faint of heart. I mean, think for yourself. Initially, we are idle. Oh, but when are we idle? When we are on ground. From idle, we can walk. But again, to walk, we need to be on ground. From both idle and walking, we can jump. Oh, but to jump, we also need to be on the ground. When we are on the air, we can move, but we cannot walk. And when our jump ends, we need to go back either on the walking state or an idle state, depending on if you're moving in the air or not. Then, we also need to factor in attacks. We can only attack when we're on the ground, especially in the idle or walking state. When our attack finishes, we need to go back to idling or walking. Oh, and we cannot jump while we're attacking. As you can see, this can become cumbersome pretty fast. And I've not even talked about half the states that the player can be in. So, state machine it is. If you are still not convinced by my explanation, I will leave a link in the description below containing more of the reasoning behind as to why I decided to go with state machine. Anyway, moving on, we will firstly code in our state class. This class will actually hold the code required to run any state the player can be in. By state, I mean the walking state, the idle state, the jump state, etc. etc. As we know, Godot has two process functions that run for each frame of your game to update the game's status. One for a physics that run at a constant 60 frames per second, and the other for every other situation which runs for as many frames as possible per second. So naturally, we will be using these two functions in our state class. Thirdly, another function to handle all our inputs from our keyboard and mouse. Next, we will have two other functions called enter and exit, and will run whenever we enter or exit our state respectively. Now, they can have n number of use cases, like running an animation at the start of the state, like when we enter our idle state, we want our idle animation to run, etc. etc. Speaking of entering or exiting a state, to transition between states, we'll have our three body functions return a state as their return value. This return value will be used by our state machine class to transition between other states. How so? In all three of these body functions inside our state machine class, we will run the corresponding body function of our current state and save its return value inside our variable. If this variable is not null, we will change our state to this new one by running our current state's exit function, change our current state to this new one, and then run its enter function. This is a basic pseudocode of our state and state machine classes. Now let's get into actual coding. First, we will code in our base state class. As you can see, here are our enter and exit functions, as well as the three body functions that will return a state. Next is the state machine class. First, we will define the starting state. This will be the state that a character will be in at the start of the game. Then we define our current state variable, and then the three body functions that will run the corresponding current state function and store its result, that is a new state, in another variable. When this variable is not null, we will change our state machine's current state to this one. And finally, we will initialize our state machine by running the change state function using the starting state as its parameter. This will make our current state to be our starting state. Initializing the character, we will then import the state machine into our player's node tree and then begin writing the player's code. The player's code is pretty simple. In it, we will run our three body functions inside Godot's actual process and input functions, and then initialize our state machine inside our ready function. Now, we will write our player state class. This refers to the state that our player will be in and will inherit our base state class, so that we are able to use all our state classes function here. The only thing different in our player state will be the reference to our player, which we'll get by getting the reference to the first node in our players group. Before moving to the last part of our video, that is writing our idle state, we will first make our animation player node and add in our idle sprites there from our animated sprite 2D to create an animation out of them called idle. Now we can start writing our idle state. This will be another class called player idle state and will inherit our player state class. The only thing we will write in this class for today will be to play the idle animation during its enter function. And with this, our coding is done. Add in the reference of our starting state to be the idle state. And here is the final result. Pretty cool, right? At the end of this video, you will have a character controller that can not only move but also jump using State Machine. If you do not know what State Machine is, watch the part 1 of the series. Now, let's start by diving into a player. Make a new node called walk and attach a script to it. This script will hold our walking state code. However, before writing our code, we need to do some prerequisites. One is to add the name of our walking animation, similar to what we did for our idle animation. Second, add the variables to our corresponding corresponding state. This will help us when we will transition between states, make them exportable so we can edit them in the editor, and finally add the variable for our movement input key. We will use this to move left and right, map to A and D of the keyboard respectively. We will then have our idle state transition to work state whenever any movement key is pressed. To test our changes still here, we can add a print log to our work state's enter function, run the game, and see that the work state has been entered. Great, but now as you can see, we have yet to add any animations to our work state. So let's do that. With our animation now set, let's try to actually move our character. For that, we make a variable for our walking speed and start writing the code for our walking physics. Speaking of physics, since we will be dealing with gravity, let us change our player state's physics process function to apply the gravity to our player. This way, we can simply inherit this part for all of our states instead of writing it separately for each of them. Inherit this function to our idle and walk state, and we have gravity. Now, let's write the script to facilitate player's movement. Our doMove function will move the player with move speed along a particular direction. To get this direction, we will make a separate function called getMoveDir and make a new input mapping for our left and right direction. Similarly to our movement key, add these action names as variables to our player state and use the getAccess method in our input class to get our corresponding left and right direction vectors. Test it out. Great, everything works. We now add in the transition to our idle state once we have stopped moving. With this, our basic walking code is done. Now, let's see how we can make our character flip its sprite to face the moving direction. For this, in our player state class, we will have a sprite flip boolean. This will hold the check to see if our sprite is flipped or not. Next, we will make a function that will determine when and how to flip the sprite. Speaking of when, we will see if our sprite can be flipped when we have pressed the movement key or when we have changed our direction. We will also need to pass along this sprite flip variable across our states. Since we will be primarily flipping our sprite when we have pressed our left or right key, we will be working very closely to our current input in our determine function, which is primarily the left and right one. So, of course, we will need a variable that will store our action keys to these particular input mappings. Looking into the documentation, we can see that action get events is exactly what we need. An array of input events corresponding the particular action name, which in our case will be the left key and the right key. Let us print it out for you to better understand what this function does. As you can see, we get an array of input events corresponding to our left or right keys. However, as you can also see, the value in the array is not entirely equal to the event that has occurred right now. Primarily in our array, we have A physical, whereas we have pressed the A button. Now why this happens is a topic for another video, but for now, we can just simply slice this particular string. And voila! Our values are now equal. Since our sprite is by default facing the right direction, we will flip our sprite when we are facing the left direction, which we can easily do by calling our left array's find function, and similarly so for our right array. To flip our sprite, we just change our sprite's flip edge property to be the same as our boolean variable. To use this function, we just simply call this when we have pressed our movement key in both our idle and walk state. Now, we need to pass along this sprite flip value across our states. You will notice that our player is pretty much working perfectly without this addition as well. However, this is because we have not added any other states. If we will add more states like jump, punch, kick, etc., which we will later down the line, state management gets a lot tougher due to inconsistent values across shared variables, so we will have to do this step anyway. So better to do this now only. And then again, it's pretty simple once you get the hang of it. For this, we will have to change our base state class, particularly the exit function, to take in an optional parameter called the new state, referring to the state that we will transition into, and subsequently pass along our variables. Now it is just a matter of trickling down this change down our state machine and player state class with just one extra step for the latter, that is passing along the value of our sprite flip variable. Now we just inherit this function across our idle and walk states. With this, our player now can walk and change its sprite. Just a reminder, if you like this style of video, that is, my devlogs and how-to videos, do consider subscribing to this channel. It motivates me a lot in making videos and also the YouTube algorithm to reach a wider audience. In this video, I will tell you how you can make a variable jump for your 2D character controller using state machines. If you do not know what a state machine or character controller is, watch the part 1 of the series. But first, let me tell you what a variable jump is. It simply means that you will jump higher if you are holding the jump button as compared to just pressing it. Now, let us have a quick glance at the logic of our code. We will be actually programming 2 states, one for the jump and one for the fall. Whenever the player presses a jump button when we are on the ground, we will enter the jump state. Upon entering, a jump force will be applied to us. And when we release our jump key, we will make our vertical velocity to be 0, essentially removing any of the jump force still being applied to us. If it has not been already taken care of by the gravity. Now, as soon as our velocity turns negative, we will enter the fall state, where gravity will do its magic and throw us onto the ground. Understood? Great, let's start. First, we will set up our player jump and fall animations. Since it is not the main part of the video, I will just skim over it. And moreover, I have already taught you how we can do this in our part 1. Make a jump state node and attach a script to it. Here, we will define 2 variables, one for our jump force and the other for our movement speed in the air. Now, before we go any further, we need to do some prerequisites. These are the same as what we did for our walk and idle state. That is, adding the variables to our jump and fall animation name and input mapping for our jump button. And 2 player state variables referencing the node of our jump and fall state respectively. Next, we apply our jump force when we enter the jump state, and cancel it out when we release the jump key. Now, since our vertical velocity is 0, we need to enter our fall state. However, instead of writing the check here, we will go back to our base player state class and add the condition that if our vertical velocity is greater than 0, we have to enter the fall state. Anyway, now we just simply return this super function in our jump state and connect our fall state node to the value of the fall state variable, which we forgot to create, so let us just do it now. Same thing, make a fall state node, attach a script to it. We have already done this before. The only thing different is instead of inheriting our player state's physics process, we will be writing our own. This is because we cannot have fall state return itself every frame, as it might lead to unwanted recursion. So, just apply the gravity and the transition to the walk or idle state when we are on the ground, depending on whether are we moving or not during that particular frame. And with this, we are done. This video is divided into 3 sections. One, where we will import our attacking animations and code it into our player. Second, where we will add our hurt boxes and hitboxes to actually register our attacks and damage. And finally, the third part, where we will add the game juice to our attacks. That is camera shake, camera zoom, in order to make our attacks punchy and satisfying to hit. Okay, let's start. First, let us import our punch and kick sprites from our asset pack. These sprites will be used to make our animations later on. Adding sprites is a very simple process using animated sprite 2D. Interesting things happen when we start writing our animations. Starting now, we have 2 main attacks, namely punch and kick. For punch, I envision it to be a very quick attack with a low damage. By quick attack, I mean that it has a very small startup and recover window. Post-editing with here. Some of you may not know what a startup or a recover window is, so here's a quick small guide. Startup window or startup frames are the frames required to start any action, which in this case is a punch. I mean, you do it in your real life as well. Imagine yourself punching. You just don't go shoosh and punch. You first wind your hand back, tuck in your elbow, and then punch. This is essentially your startup frame. Our player will have something like this as well. Now, recover frames on the other hand are the frames required by the player to recover after performing certain action, which again is our attack here. Again, referring back to our previous example, after you punch, you just do not go back to normal. I mean, you take in a few short breaths, put your shoulder back in the correct position, and yada yada. Our player will again do the same. Startup and recover frames are essentially there for you to get punished for spamming your attacks, as you are pretty vulnerable to incoming attacks during this phase. Okay, Back to the video. Kick, on the other hand, I envision it to be a very slow attack with a high damage output. Again, by slow, I mean that it has a very large startup and recover window. We will see both of these in details when we wire our animations. Now, let us add in our punch animation. Notice that the animation is 3 frames long. The first is our starter frame, the second, our active, and the last one, our recover frame. Now, moving on to our kick animation. Here now, you will notice a stark difference between the animation lengths of these two attacks. As you can see, the kick is nearly double our punch animation's length, with the first 2 frames being our starter frames, the next 2 our active frames, and the last 2 our recover frames, making this a slower attack as compared to our punch. With this, our animation is done. Now, let us move on to the coding part. The coding actually is pretty much same to what we did in our previous videos, with just a small caveat which I will mention later on. First, let us go over our punch state. First, let us do the prerequisites. I sound like a broken record at this time, as I have repeated this over and over again. First, add in our punch animation's name as a variable, then the punch state, and finally, the input mapping. That is the button that will actually cause us to punch. Now, here is our basic punch script that we will edit. This script is pretty much similar to what we have done previously. We play our animation when we enter our state, and these are the states that we will transition to once our punch stops. The only difference is how do we know when our punch has stopped. For this, we make a variable called #attack. That is initially false and will only become true once our punch animation ends, indicating that our punch has stopped. Once we have attacked, we will automatically go to our idle state, or to any other state if we have pressed the corresponding action key. Wire the transition to our punch to our idle and walk state, and yeah, we can punch. Kick state is the same as our punch state. Nothing much to narrate, you have seen all of this just a minute before. Instead, I would like to take this opportunity and ask you a little question about the channel. You see, this series is pretty much at the end. I will just make one more video about pain and death state, and that is pretty much it. My question is, what about later? Do I go back to making my devlogs of the video games I have made? And I assure you there are tons of good projects that I want to make and show you guys. Or I pick up another tutorial series and make tutorials on them, namely making a retro 3D FPS on Godot, similar to the likes of Doom or Quake. Please mention your thoughts down below in the comment section. Anyways, on to the video. For our hitboxes and hurtboxes, we will define 2 area theory class scripts. One being the hitbox and the other being the hurtbox. The logic behind the hitbox and hurtbox is that our hitboxes lie in certain collision layers and our hurtboxes listen to these collision layers. So, whenever these 2 boxes collide, the hurtbox gets a signal that something has entered its area. That something is our hitbox. Once registered, we deal the damage to the owner of the corresponding hitbox. So, the code is pretty simple. In our hitbox, we will define its collision layer to be 2 and its collision mask to be 0. That is, it has no collision mask. 2 is just any random collision layer that I decided on the fly. Our hurtbox will be just the reverse. That is, its collision mask will be 2, while its collision layer will be 0. Next, we will define a function that will run when someone has entered the area of the hurtbox, and if that entered area is a hitbox, we will deal damage to it. The exact logic of dealing damage to the player will be done in the next video, along with the pain and the death state. For now, we can just print to the console that the damage has been dealt. Now, all you have to do is to define our hitboxes inside our punch and kick state, and only make them active during the corresponding active frames of our animations. Everywhere else, they will be disabled. To test our hitboxes, let's make a dummy hurtbox inside the level, and yeah, we are dealing damage. Except for one small thing, our hitboxes are not rotating with the player. That is, they are only facing the right direction. The fix for it is pretty simple. If our player is slipped during the entrance of our attacking state, we will change the X component of our hitbox's scale to -1 or to +1 otherwise. And with this, we can now deal damage. Well, there are various aspects to game juice. Here, in this section, we will look at 2 of them. They are very low effort, but in my opinion, improve the enjoyability of our game tremendously. These are camera shake and camera zoom. And we will use the camera nodes, zoom and offset property to manipulate them. Both of them have the default value of vector 1 and vector 0 respectively. So, let us define them in our camera class. During the start of our game, we want our camera to inherit these values. Next, we will write two variables representing our current zoom and shake levels. Two float variables that will determine the factor by which we will change our current zoom and offset variables to their initial values. First, let us look at our camera zoom code first, as it is relatively simpler. Every frame, we will lerp our current zoom, the initial zoom value, using our frame delta multiplied by our zoom recover factor as the step, and then assign this value to our actual camera zoom property. How it works is that majority of times our camera zoom and our current zoom will be same. So essentially, this code will have no effect. However, when we change our current zoom to something else, this function will kick in. Namely, we will lerp our current zoom back to its initial value using our step. This way, over time, our current zoom will become equal to its initial zoom value, bringing our camera back to normal. We will make a small function that will be called by other bodies to change our current zoom variable. Now, to use this code, I firstly add our camera into a group. Next, add this camera's entry into our player state class. Next, when we punch or kick, I just call the zoom function and change its value to be something greater than 1. Now, we test the code. And voila, everything is working. Now, on to screen shake. The setup is pretty much similar to our camera zoom code. So I'll just explain the logic behind camera shake. During our recovery phase, that is from any given offset value to the initial one, we will randomly vary our offset across its positive and negative scale along both of our x and y components. This will make our camera teleport to random points in every frame, simulating a shaky effect, which is our camera shake. Adding this to our punch and kick script, and voila, we have camera shake. In this video, I will tell you not only how to deal damage to the player and add a knockback force to it, but also how adding a little bit of game juice can elevate all of this process to the next level. Okay, let's start. First, let us go over how we can deal damage to the player. For that, we go back to our hurtbox code. In here, I will actually make a derivative class called player hurtbox. This class will be responsible for transitioning the player to the damage or the pain state. And this transition will trigger whenever any hitbox enters our hurtbox area. Adding this is pretty simple. We just update our onAreaEntered function. How? We keep everything the same except that whenever any hitbox comes to us, we will call our state machine and specifically its change state function with our pain state as a parameter. Speaking of pain state, the code is pretty much same as our punch and kick state. That is, we enter our state, run an animation, and as soon as our animation ends, we go back to our idle state. Just in this case, our animation is our pain state animation. Integrate it all up, and here we have our pain state working. Now, let us quickly add our knockback. For this, we add another variable in our player hurtbox called the hitting area. This variable will store the owner of the incoming hitbox, and the reason behind this variable will be told to you shortly. Go back to our pain state and add a function called knockback. Now here we will use our hitting area to get the direction vector of the incoming attack. This way we can ensure that the knockback force that will be applied to us is in the direction of the incoming attack, so that we are pushed away from it and not pulled towards it. Apply the force, call this function in our physics process function, and update our exit function to remove this force whenever we exit our pain state. And with this, our knockback is also done. And now, moving on to the bonus game juice. In this bonus section, we will learn how we can slow down the time whenever we get hit. This allows us to accentuate any attack that the player takes. The logic behind is that our Godot engine runs on a time scale of 1 by default. If we decrease this value of 1 to say 0.5, our game's time will be slowed to half its value. And on the other hand, if we increase it to say 2, we will play our game at 2x the speed. Go back to your hurtbox code and add a function called engine slow. This is here where we will slow down the game's engine speed. So here, let us just put any value shorter than 1, add a timer to our code, that is the time till which our game's engine will be slowed, and when the timer runs out, we just turn back our game's time scale back to 1. And with this, we are done. And moreover, done with this tutorial series as well. Now, you're equipped with everything you need to know to make a successful fighting game. Hope you like this series, guys. Do not forget to like and subscribe. Okay, bye-bye.